so we're going to do a lab on the wave nature of light. So in the late 1800s, a guy named Thomas Young did an experiment to prove whether or not light was a wave or a particle. Now Newton saw it as a particle, a stream of particles, and a guy named Christian Huygens saw it as a wave. And so Thomas Young did an experiment in the 1800s. It was very simple, but it basically proved that light did behave as a wave. And I think it's important that you notice I use the word behave, because it also behaves as a particle, and we'll get into that in a later video. So let's just talk about the wave nature of light. So this is a clip from the video I really wanted you to watch from the PowerPoint from this week. If you haven't watched it, go do it. It's the one from Veritasium. But this is the point where he's making waves on the water. And so he's got two sources of waves, two sources of ripples. And it is showing this interference pattern. If you look closely, you can see it. The waves are coming together. They're destructively interfering here and constructively interfering here. Interference is a wave property. And so if you can prove that light interferes with itself, then you can prove that it does behave as a wave. Okay, so I've got this laser pointer here and some pieces of hair. So I'm going to split the light beam with a piece of hair, cause diffraction, and then the light will interfere with itself. So let me turn off some light sources here so it doesn't. So that green laser beam, which you see on the wall, will go through the hair. So I'm going to send it through regular hair first. This is human hair. And if you look on the wall, you can see the pattern on the wall. So if you look, you can see that the wave, or the light, is in fact interfering with itself and creating these patterns on the wall. Okay, so that's shown through human hair. Okay, the next one, I will shine it through horse hair. That's what I have in the middle. And it will split it. Let's scoot it over a little bit. There we go. Now, you'll notice this is the beams, the fringes are a lot closer together. To get way in here, look this time, you still have the interference patterns. They're a lot closer together. Okay, but you can easily see that the light is hitting the slit. It's a double slit. So if you think about hair, the light has to bend around it, and so it's the same as sending it through a double slit. And the light diffracts around that slit and interferes with itself, creating this pattern. Now this is a very simple demonstration, but you have to understand Thomas Young didn't have a laser pointer to shine this through and show. So he actually used sunlight, which showed some different things, because sunlight is composed of all light. So if I use red, okay, you might notice a slight difference in how the beam splits. So notice with red, you get a little bit different sized gaps. This is back through the human hair. A little bit different sized gaps than you got with the green. So if I can make this work, I could shine the red and the green at the same time. I'll put the green on there, over on the screen. You see the green on here. Just kind of get a mental picture for the gaps. And then you can see the red right there. You notice they're not gapped exactly the same. So it does depend on the wavelength of the light as well. Now, that is with hair. So if I use a diffraction grating, this diffraction grating has multiple lines per slit, or as I shine it through the 100, notice the interference pattern there. Much easier to see, much more pronounced. Okay, that's with 100 lines, and then here we have 300 lines per centimeter, 100, 300. So as there's more slits, or the slits are a lot closer together, you have a much more pronounced effect. So this proves that light does in fact behave as a wave. Okay, I shine the green one too, get a feel for how that looks. So this is in the same spot. Notice green, think about the difference in the gaps, and then red. Green, green, red. So the color of the light does make it have an effect as well. All right, so back to this. So we have the same effect. We show the water waves. Water waves do the same thing as the light. This proves that light does behave as a wave. So if you have, with water, you have the same thing. You have constructive interference, destructive interference. So with the slits here, you had constructive interference and destructive interference. So you have the water waves, constructive, destructive. You have the light, constructive, and then you see the gaps. That's where the waves are destructively interfering. Okay, so there's what it would look like. You have a source of light, goes through a slit. This is basically what a laser does, and then I send it through a double slit. This whole thing here would be the hair, and then you have a spot where you have maximum interference, which you see the bright bands, and then minimum, and a maximum, and a bright, and a minimum, and a maximum. And you can see it clearly. All right, so another way you can test to see as light as a wave is with polarization. So I'm going to turn the light on in the classroom. And if you've ever played with polarized sunglasses, you will notice that if you twist them, rotate them 90 degrees relative to each other, you will get a full cancellation of the light. So if you picture light as a wave, with the wave, it is happening at multiple angles as it goes through. As you send it through a polarizer, you will notice that it dims the light that comes through. Send it through another polarizer, you have them the same way, nothing happens. But as you tilt one, you will notice that it totally blocks all the light out. And it does that because of this right here. One polarizer is vertically aligned and the other is horizontally. And so if you cancel all the light out, you get no wave and nothing comes through. Okay? You can also see some interesting stuff when you put these up to the screen. Notice how they turn different colors because we have white light there. And this has to do with different forms of polarization, but the idea is still the same. And so this is our current understanding of a ray of light, a wave of light. They carry energy, and they all move at the same speed, obviously, all electromagnetic waves. But you have an electric field that then produces a magnetic field that then produces another electric field, and so forth. And this only happens at one speed, which is the speed of light. It won't work unless it's moving at that speed, really fast. Light can travel through anything, doesn't need a medium, so it doesn't have to go through air. It can go through space, and it's created by the vibrations of an electric charge. So you vibrate an electric charge, that produces a magnetic field, and then that magnetic field then produces an electric field, and the whole thing reproduces itself as you keep vibrating that electric charge. So just like all waves, starts with a vibration, but an electromagnetic wave is an electric charge vibrating. All right, so that is waves.